Okay, in this video we're going to talk about section 4.8, dealing with Newton's method. Okay, and we're going to be finding the approximation. We're going to be approximating roots of a function using Newton's method. Okay, so here, a common problem that arises in mathematics is finding the roots or zeros of a function. The roots of a function are the values of x that satisfy the equation f of x is equal to 0. Equivalently, they correspond to the x-intercepts of the graph of the function f of x. And pretty much we've been seeing an important example of a root finding problem. So to find critical points of a function f, we have to solve the equation f prime of x equal to 0. That means the roots of f prime are going to be your critical points of f. Newton's method is one of the most effective methods for approximating the roots of a function. So that's the basis of section 4.8. All right, Newton's method is mostly derived geometrically. So here we're going to assume that R is a root of f that we wish to approximate. This means we want to find f of R equaling to 0. So we assume that f is differentiable on some interval containing R. And suppose x sub 0 is your initial approximation to R that is generally obtained by some preliminary analysis. And a better approximation to R is obtained by carrying out the following two steps. And that's this. A line tangent to the curve y equal f of x at the point x0, f of x0 is drawn. And then the point x1, 0, at which the tangent line intersects the x-axis is found, and x1 becomes your new approximation to R. So in this case right here, let's say I have this graph of y equal f of x. And let's say here that x of 0 is over here, and we're just picking x of 0 here as a initial approximation to R. So in this case here, what I'm going to do is draw the point that is the y value on the graph of y equal f of x. So here's x of 0, and this would be the point on the graph that corresponds to x of 0. That would be this point right here. So I'll go ahead and draw that point there. And then next I'm going to draw a tangent line going through that point. Keep in mind the tangent line is the line that touches the graph at that point. Okay, so here's my tangent line that I'm going to draw right here. Now the point where that tangent line intersects the x-axis, that's going to be my new approximation, x1. All right, and then next, I'm going to draw the point where x1, the corresponding y value for x1 is. So at x1, we have this point right here. So here's x1, and here's the point on the graph of y equal f of x that corresponds to x1. Now I'm going to draw the next tangent line that touches that graph. And it's going to intersect the x-axis at this point here, which I'm going to call x2. And then I'm going to draw another point that corresponds to x2, and that's on the graph of y equal f of x. So here's that point right there. Now x2 is my new approximation. The point at x2 is right here on that graph of y equal f of x. And now I'm going to draw another tangent line. And that tangent line will cross the graph on the x-axis. So So that would be x3. That would be my new approximation. Okay, so pretty much you can get the idea of what I'm getting at here, because the more tangent lines that I continue to draw, the closer and closer I will get to what the zero of that function is, which is in this case going to be r. Okay, and this continues on the next page. So we want to improve the approximation of x1. We just repeat that two-step process using x1 to determine the next estimate, which is x2. Then x2 will be used to obtain x3, and so on. So if we continue in that fashion, we will obtain a sequence of approximations x1, x2, x3, and so on, that ideally get closer and closer or converge to the root, which is your r. Okay, and several steps of Newton's method and the convergence of the approximations to the root are shown here in this figure, so you can see what's going on here, because as the more tangent lines I draw, the closer I will get to the root for that function, which is r. Okay. Now, what's left is just finding the formula that captures this process that I just got through talking about here. Well, let's start off with that point-slope form for a linear equation. And that is, of course, y minus y1 is equal to m, which is your slope, times x minus x1. Let's say we had this ordered pair, x of n and f of x of n. Okay? So in other words, x of n will be x1, and f of x of n will be y1. So if I do some substitution here, this is what I have, y minus y1. I'm going to replace that with f of x of n. Now keep in mind, when you're finding the slope, you're actually finding the first derivative of that function, and that will help you determine the slope of that line or of that curve. So I'm going to replace this m with f prime of x. That's this notation. Times x minus x1, I'm going to replace that with x of n. And of course, in this case, we're finding the x-intercept. When you're finding the root of a function, you're finding the x-intercept. So that means our y value will have to be equal to 0. So I'm going to replace that y with 0 minus f of x of n equaling to f prime of x times x minus x of n. And 0 minus f of x of n will just be negative f of x of n. That's equal to, and I'll just bring down f prime of x times the quantity x minus x of n. Now what we want to do here is get x of n by, well, just get x by itself. Just get x by itself. So the first thing I need to do here is, since I'm multiplying this by f prime of x, I'm going to divide both sides by f prime of x. So that means I have x minus x of n. That's equal to negative of f of x of n minus f prime, divided by f prime of x of n. And then to solve for x, I will move over that x of n over to the other side. So here I have x of n in front minus f of x of n divided by f prime of x of n. And that will be equal to x. Okay. And here that x will be the next approximation. So I'm going to replace that x with x of n plus 1. That's going to be equal to this. X of n minus f of x of n minus f prime of x of n. So this right here represents what Newton's method is. Okay? So here, this is just the formula for finding the next approximation, x of n plus 1. So on the next page, you will see what that is. This is Newton's method for approximating roots of f of x equal to 0. So the first step would be to choose an initial approximation x of 0 as close to a root as possible. Now, in these examples that I will be doing in this video, you will be given an initial approximation to start off with. And then number 2, for n is equal to 0, 1, 2, and so on, this is the formula. X of n plus 1 is equal to x of n minus f of x of n divided by f prime of x of n, with the provision that f prime of x of n is not equal to 0. And then number 3, your n calculations when a termination condition is met. In other words, when your value of x of n plus 1 is the same. Okay? So here, Newton's method is an example of a repetitive loop calculation called iteration. So you're going to be doing as many iterations as you can until you get the same value for x of n plus 1. The most efficient way to implement the method is with a calculator or computer, and I'm going to show you how to use the calculator shortly in this video. This method is also included in many software packages. All right, so if we start with example 1, I'm going to do the long way with this one. And then the remaining examples, I'm going to show you how to use the graphing calculator to do these types of problems here. All right, let's say we got f of x equals to x squared plus 4x minus 32. And our initial approximation will be x of 0, that's equal to 6. Okay, we want to write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2. So all we want is just the first iteration and the second iteration, which is x1 and x2. So here's what we got. Here's what we're going to do here. Our x of 0, that's 6, so that means your n in this case is 0, and those I do have the table that will help you come up with x1 and x2. xn, or x of 0, that's going to be 6, so that 6 will go here. Now I need two things. Well, I got f of x, but I need f prime of x. Well, let me rewrite f of x is equal to x squared plus 4x minus 32. F prime of x, if I take the derivative of this, this is going to be 2x plus 4. Okay? And now we're going to use this right here, that x of n minus f of x of n divided by f prime of x of n. And personally, I don't like those x of n's. I just keep it simple and just use x. So that means here, of course, x of n plus 1, that's going to be x minus f of x, that's the x squared, plus 4x minus 32. That's divided by f prime of x, that's the 2x plus 4, okay? F of x divided by f prime of x, and then we're subtracting it from x. Okay, so we're going to use this table to help us complete those numbers that we're looking for in this case. We want x1 and x2, so here's what we're going to do. F of xn. Well, f of x is that x squared plus 4x minus 32. So using our calculator, we'll just replace each x with this 6. So using the calculator, we got this. Clear this out. I'm going to put 6 in parentheses, and that's going to be squared plus 4 times x, which is 6, and then minus 32. I'm substituting every x in f of x with 6. That would give me 28. So that 28 goes in this box here. And now f prime of x, I want f prime at x equals 6. And f prime of x is at 2x plus 4. So I'm going to substitute that x with 6, so it would be 2 times 6 plus 4. That will equal 16. So f prime of x, that's 16 here. Now the next column is f of x of n divided by f prime of x of n. That's going to be this number, which is 28, divided by f prime of x of n. That's this number right here, 16. So if I do 28 divided by 16, that will give me 1.75. Okay? And then finally, in this last column, x of n minus f of x of n divided by f prime of n. Well, x of n is this 6. F of x divided by f prime of x, that came out to be 1.75. I'm going to subtract this number minus this number. 6 minus 1.75. So 6 minus 1.75, that would give me x1, which is 4.25. So x1 will be 4.25. Now we're going to find x2. To find x2, I'm going to take that x1, which is 4.25, that's going to be my new approximation. So this n will be 1, because that's x1, and then the 4.25 goes under x of n. So this right here goes here. And then we repeat that process here to get x2. So for f of xn, well, f of x is that x squared plus 4x minus 32. So here's what I'm going to do. Take 4.25, and then that's squared. I'm replacing every x with 4.25, and then plus 4 times x will be replaced with 4.25 minus 32. This ends up being 3.0625. So f of xn is 3.0625. And then f prime of x of n, well, x of n is 4.25, and f prime of x is 2x plus 4, so we'll replace the x with that 4.25. So it'll be 2 times 4.25, close parentheses, plus 4. That gives me 12.5. So 12.5 goes here. And then f of xn divided by f prime of x of n, that's going to be this number divided by this number right here. I'm going to take that 3.0625, divide that by 12.5, and then hit enter. Here I get 0.245. And then finally, the last column, x of n minus f of xn divided by f prime of xn. That's this number subtracted from this number right here, 4.25 minus 0.245. I end up with 4.005. So this represents x2. So x2, that value is 4.005. And if I wanted to, I can come up with x3 by making this be x2 and then go through that whole process. But they only want x1 and x2. So these are the approximations for those two. x1 will be 4.25 and x2 will be 4.005. Okay. Okay, here's a second example, number 2. In this case, I'm going to use the graphing calculator and show you how to come up with your iterations here. All right, so here I want to write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2. And in this case, I get f of x is equal to 3 to the negative x minus 14x, and x of 0 is equal to the natural log of 5. Okay? So x of 0, that's your n, is 0. X of 0, that's what this is, ln of 5. Now, first of all, I got f of x, but I need f prime of x. And I need my equation, or my formula, for Newton's method. Well, if f of x is 3e to the negative x minus 14x, then f prime of x, if I do this, I bring down the 3, e to the negative x, its derivative is e to the negative x, but I need to apply the chain rule by taking this inside derivative. The derivative of negative x will be negative 1. And I'm going to put the negative sign in front. So it'll be negative 3 e to the negative x. And then minus the derivative of 14x would just be 14. Okay? So that's what f prime of x is going to be. And of course, x of n plus 1, I'll just use x here, and then minus f of x, which is that 3e to the negative x minus 14x, divided by f prime of x as negative 3e to the negative x minus 14. And in this case here, that is going to be my formula for Newton's method. All right, now I'm going to show you how to use the graphing calculator to type in all this information that I have here. Now we do have the x of 0 that's given to us. That's going to be equal to the natural log of 5. We're going to enter this in the calculator first, so I'm going to give you the keystrokes first. You want to type in ln, and then type the number, press the number 5, and then close your parentheses. Now you're going to press the button that says STO on the far left-hand side, because you want to store this in x. So you'll press xt theta n to store it in x, and then you'll hit enter. And feel free to pause this video if you want to write down those keystrokes. Okay. So here's what we have. You want to press the ln key, which is on the far left-hand side. That gives you the left parentheses. Press the number 5, close parentheses. And then you're going to store this. And I'm going to zoom out a bit so you can see what I'm doing here. I'm pressing the button that says STO on the far left-hand side to store it in x. So you'll press xt theta n for the x. And then you're going to hit enter. It will give you the decimal approximation for the natural logarithm of 5. But, of course, it is stored in x. Okay? Now I'm going to zoom back in a bit. We're going to enter this expression right here. And I'll rewrite it as x minus. And I'm going to put the 3e to the negative x minus 14x in parentheses. And that's going to be divided by, and then the denominator will be in parentheses, negative 3 negative 3 e to the negative x minus 14, close parentheses. Now, here are the keystrokes for that. First of all, for the x, you have to press xt theta n for your x, and then minus left parentheses 3. Now for the e to the x, you'll have to do second, and then the ln key, because right above the ln key is e to the x. And then press the negative key, which is at the very bottom of the calculator, and then xt theta n for the x. And you want to press your right arrow key to get out of that exponential part. That's right arrow to get out of it. And then minus 14 xt theta n to get your x. And then close the parentheses. That's just the numerator right there. And then that's going to be divided by, now this is your denominator down here, so we're going to left parentheses. Then you're going to press your negative key, which is at the very bottom, 3, and then press the second key, and ln to get your e to the x. Second ln gives you e to the x. And then you're going to use your right arrow key to get out of the exponential part. And then press your negative key. And then xt theta n for the x minus 14. Close parentheses. So that's your denominator right here. After that, you're going to press STO because you're going to store that in x. And then press enter. This will give you the first iteration, which is going to be x1, and then we need x2. I'll show you how to get that shortly. Okay, so let's start with this right here. We've already got this stored. Now we're going to go ahead and enter this in using our keystrokes here. And do pause the video if you need to. We'll start with the xt theta n for the x, minus, then left parentheses, 3, and then second ln for e to the exponent. Then you're going to press your negative key, and then x. You're going to use that right arrow key to get out of that exponential part, and then minus 14 xt theta n for your x, and then close the parentheses. And then that's going to be divided by, so you'll press your division key. The denominator will be in parentheses, so left parentheses. Press your negative key. Here's your negative key down at the very bottom, so you'll press that. Okay, so let me zoom out if you need to see it. Your negative key is at the bottom. And then your 3. Second ln for the e. And then press your negative key, and then xt theta n for the x. And use your right arrow key. I think I got this one backwards here. So here, right after you do xt theta n, then you do your right arrow key to get out of it. Okay. Okay, that was my mistake. Because you have to enter the negative and then your variable, and then use your right arrow to get out of it. And then close the parentheses. I'm sorry. 3e to the negative x. I'm sorry, go back. Minus 14. And then close your parentheses. Okay. And after that, you press the STO button to store it. And then xt theta n. And then finally, press enter. So this will give you your decimal value, your first approximation. To to 6 decimal places, it will be 0.107237. So that's what x1 is going to be, 0.107237. Now to get x2, it's going to be quite simple. All you have to do there is just press enter. That will give you the next iteration, which is in this case to 6 decimal places. It'll be 0.17873. This is a 2 here. The 9 will make that 2 or 3, so it'll be 0.33. Okay. So that's how we get the second iteration here. All right, so to answer that question here, and I'll put x1 here over here. X1 is approximately 0.107237, and x2 is 0.178733. Okay. And again, feel free to refer to this video again if you need to look at this again. You can always pause and rewind back. Okay, example 3 looks like this. And we're going to use a calculator as well. So here we're going to use a calculator as indicated here, or a program to compute the first 10 iterations of Newton's method when they are applied to the following function with the given initial approximation. So here our f of x is x squared minus 23, and our initial approximation, x of 0, is going to be 5. So we're going to be looking for 10 iterations here, from x1, x2, all the way through x10. And you can see here in this chart I have 10 rows here listed. Okay? Our n, we start off with a 0, because that's x of 0. Our x of n, or x of 0, that's going to be 5. So we put the 5 there. All right, so here's what we're going to do, how we're going to type this into our graphing calculator. Now I'll put the keystrokes down here at the bottom. Oh, before I do that, I cannot do this without finding out what our first derivative is. Our f of x is x squared minus 23. That would mean f prime of x will have to be 2x. And if that's the case here, x of n plus 1, that would be x minus f of x, that's x squared minus 23, divided by f prime of x, which is 2x. And you know what? I'm going to do something here. The numerator and the denominator will be in parentheses when we do our keystrokes for that expression, or for that formula for Newton's method. So let's start by storing the 5 in x. So first of all, for x of 0, which is your 5, that's your initial approximation, you're going to type in to your calculator these keystrokes. The number 5, press the button that says STO, and then xt theta n to store it in x, and then press enter. Okay, so I'm going to clear this, and then I'm going to press the number 5, and then there's a button that says STO, you'll store that in, press the xt theta n for your x, then enter. You'll get the 5 back, but keep in mind it is stored in x, so that part's done. Now we got to do this part right here. Enter this expression right here, that x minus x squared minus 23 divided by 2x. So for that, here's the keystrokes to type that in. First of all, it'll be xt theta n for the x, and then minus. Now, the numerator is going to be in parentheses, so left parentheses, you'll get your x for the variable xt theta n. Then you're going to press x squared to square that x. Then minus, type in the number 23, close parentheses. That's going to be divided by, press your division key. The 2x will be in the parentheses, so it'll be left parentheses 2 xt theta n to get your x, and then close the parentheses. And then after that, you will press the button that says STO to store it, and then xt theta n to store that in x. Then finally you'll press enter, and that will give you the first iteration to begin with. And again, pause the video if you need to. Okay, so here's what we're going to do. We got 5 stored in x, so next we're going to do xt theta n, press that button, and then minus, left parentheses, x, and then squared, it'll be x squared, minus 23, close parentheses. That's going to be divided by, press the division key, and then left parentheses, type in the number 2, then xt theta n for the x, close the parentheses. Now, this expression we are going to store, so we press STO to store it. It'll give you the left arrow, and then press X, because all that's going to be stored in X, and then finally press enter. So your first iteration is just simply 4.8. So x1 would be 4.8. And then to get x2, just press enter again. That will be 4 point, and we're rounding to 6 decimal places, 7, 9, 5, 8, 3, 3. And then to get the third iteration, x3, you'll press enter again. So it'll be 4.79583. This 1, the 5 will make the 1 a 2. And then x4, you'll press enter again. Notice we get the same thing. 4.79. 4.795832. And we can, and it's going to be the same for x5. X6, x7, 8, x8, x sub 9, and x sub 10. So that tells me I have found the root, or the 0, for that function f of x equal to x squared minus 23. Or at least one of the roots for that function, f of x equal to x squared minus 23. And that's approximately 4.795832. Okay. And finally, example 4. Again, we're going to use the calculator to compute the first 10 iterations of Newton's method when they are applied to the following function with the given initial approximation. Here we got f of x equals to the natural log of the quantity x plus 1 minus 3. And here our x sub 0 is going to be 19.1. Okay. So n, of course, is 0. That's x sub n, 19.1. And we're looking for the first 10 iterations here. x1, x2, x3, x4, x5, x6, all the way through x10. Okay, so the next thing I'm going to do here, we need to find out what f of x is. Well, we know what f of x is. We need to know what f prime of x is going to be. Well, starting with f of x, that's your natural logarithm of the quantity x plus 1 minus 3. So f prime of x would be, well, the derivative of the natural log of x plus 1 would just be 1 over x plus 1. And the derivative of minus 3 will be 0. And if you were to use the chain rule here, if you did the derivative of x plus 1, it would end up being 1. So f prime of x would just simply be 1 over x plus 1. Now, here's what we got to do here. We got to come up with our formula that we're going to use for Newton's method. Our x of n plus 1 would be equal to x minus The numerator is your f of x. That's the natural log of the quantity x minus 3, x minus 1, x plus 1 minus 3. That's going to be divided by 1 over x plus 1. Okay. But I'm going to simplify this a bit. The reciprocal of 1 over x plus 1 is x plus 1. So I'm going to multiply the numerator and the denominator by x plus 1. That means I bring over this x minus. Now here's what I'm going to have. The natural log of x plus 1 minus 3. That's going to be multiplied by the quantity x plus 1. And notice in the denominator, 1 over x plus 1 times x plus 1, those x plus 1's divide out. I'll have a 1 in the denominator, so it'll just be this expression. X minus the quantity of the natural log of x plus 1 minus 3 times the quantity x plus 1. Now, let's store our initial approximation in x. So that means here, for the x of 0 equaling to 19.1, here's what we type in. Type in the 19.1, press STO to store it in x. So after STO, you'll press xt theta n for the x, and then press enter. So here's what we're going to do, 19.1, let me turn this on, 19.1, then press STO to store it, and then store it in x. Press xt theta n for your x, and then hit enter. You'll get the 19.1, but it's stored in x. Now, for this expression right here on the right-hand side, here's what we're going to do. Here's how you're going to type this in. First of all, xt theta n for your x minus, then I'm going to do left parentheses, press the ln button, and then xt theta n for the x. And when you press ln, it will give you the left parentheses anyway. And then plus 1, close parentheses, then minus 3, close parentheses. Because all of this is your numerator. And then that's going to be multiplied by, so you press the times key, and then left parentheses, because that x plus 1 needs to be in parentheses, xt theta n for the x plus 1, close parentheses. And then after that, you're going to press STO to store it, and then xt theta n, you're going to store that in x, and then finally press enter. That will give you at least the first iteration. Okay? So we got this 19.1 already stored in x. So here's what we're going to do here. Again, pause the video if you need to copy down these keystrokes. All right. Next, we'll go ahead and start off by pressing the xt theta n for the x, minus, and then left parentheses, press the ln key, and then xt theta n for your x, plus 1, close parentheses. And then you got the minus 3, so be minus 3, close the parentheses here. And then after that, press the times key, because you're going to multiply that by left parentheses, xt theta n, so you do x, get the x by pressing xt theta n, plus 1, close parentheses. And then after that, you're going to press the button that says STO to store it, and then xt theta n to store all of that in x, and then press enter. So So here is the first iteration. So our first approximation will be 19.085532. Because a 6-digit is a 1 to the right of that is 7. We'll increase that 1 to a 2. That's the first initial approximation. To get the next, which is x2, press enter, and it'll give you the next one, which is 19.085537. That would be x2. And then if you press enter again for x3, notice you get the exact same value. And it's going to be the same for x4, for x5, x6, x7, x sub 8, x sub 9, and x sub 10. So that tells me I have found the 0 for the natural log of the quantity x plus 1 minus 3. So it'd be approximately 19.085537. Okay. So that's how we use Newton's method to come up with our zeros of any function. And this came about when calculators were almost non-existent. Okay, so here these days with calculators, we can pretty much use the calculator or use some type of computer program to come up with zeros of our function. All right, so this concludes this video on section 4.8, dealing with Newton's method. Feel free to reach out to me if you have any questions about anything that was discussed in this video or any of the homework problems that are found in my math lab.